So as I was mentioning, that today's topic is from the QSC Quantum Program, Best Practices in Gain Structure and AEC. It's to provide Q-SYS installers with a better understanding of gain structure and how to get the best audio performance out of a system. If gain structure is not set right, everything downstream goes in or goes, suffers after that. We typically, there's a saying, garbage in and garbage out. Well, if you bring a good signal in and you don't get it to the right level to go through the analog to digital converters and things like that, then you struggle with issues. And there's one thing to also remember, there's no magic fix for a bad input. Like if you've got a crackly, poor quality signal coming in, I mean, there's only so much that we can do inside of the Q-SYS system there. But the idea is um, the idea is that the gain structure is the root of everything across the auto board. Any of you folks that are using our like ACPR, that's not going to function well without having your gain structure set properly. Acoustic echo canceling. If you don't have that, if you don't have your gain structure set right, you're going to have challenges with that. So there's one of the very first things, and the reason we run this every couple of months is because it's one of the things that our support people constantly tell us. So hopefully you get something from this. I'm running solo today, so if you've got questions, drop them in there into the Q&A. I will check on that periodically throughout the presentation. But for the most part, this one's pretty straightforward and good info. So here we go. All right, so proper gain structure, key component in getting the best performance. We got a typical signal level here, but I think the very first thing we really need to do is start defining some terms, right? There might be some terms we're going to use along the way here that you're not familiar with or you've heard but don't understand what they are. And we're going to kind of give you just a 100-foot view of what those are so you have a good understanding of that. So the language of audio, right? So one of the things that we want to talk about starting off, we're looking at this chart, but we've got some things on there like dBu. That is dB decibels. So decibels are always standalone, but they have to be referenced to something. So dBu is referenced to 0.775 volts. So it's 0.775 volt signal is what we're doing. And plus 24 dBu is considered the standard clipping point for professional audio devices. So think of mixing consoles, think of things that you use in the pro audio world versus consumer residential type stuff like that. And you can't pass a signal that's bigger than the power supply of the circuit you're feeding. So that's what clipping is all about. So clipping is having an input voltage higher than the maximum output voltage of the power supply, or the incoming signal sine wave is larger than it can process. And so what it does is it clips the top of that sound wave off, hence the name clipping. It's also called distortion or overdriving an input or things like that. But for the most part, that's kind of where we're at. So noise floor, if you look at the chart here, is the level of just noise that's associated with the circuit. We'll talk about when we get to the noise floor when we have microphones, but this is just an open input on an input inside of Q-SYS or whatever the case may be, right? So if this was one of our older CMIL4 cards, it would have, plus 24 dBu. The max noise floor or the max noise floor typically is around negative 81 dBu, meaning that's about where just if you turn the meter on and there's nothing plugged into that input, you're just going to see a level of just electronic noise there. And so what we would have is you have noise floor, which is the bottom, and then all the way up to clipping point. The difference between the noise floor and the clipping point is what we consider the dynamic range. So this is the allowable signal range between the noise floor and the clipping. And in this case, it's 105 dB of difference. Headroom. It generally takes about a 10 dB increase in the SPL of a signal to be perceived as twice as loud. So we'd like for our audio signal to have 20 dB of headroom in the signal that we're reproducing, right? So that's where you get to the nominal level, right? So if we clip it plus 24 dBu, then 20 dB down from that is plus 4 dBu. If anybody remembers the old VU meters on old amplifiers or mixing consoles, that that's essentially a unity gain or a nominal level. Is some people say 0, but you're only 4 dB off. But 4 dBu is considered a nominal level. So if you're that's where you want to set all your input levels to, and we'll talk more about that when we get through this. So therefore, you've got 20 dB of headroom, and then that leaves a signal to noise ratio, meaning the noise floor is at negative 81. The difference of that up to plus 4 is 85 dBu. Nominal level is just that sweet spot. In professional audio, it's their consumer line level. It's negative 10 dBV. Microphone level is going to come in at like negative 60 dB. So if you just have a standard wired mic, it's not a condenser mic, it's a dynamic mic, it's going to have a negative 60 roughly, right? Or 67, 57, 56 dBu. So there is no standard microphone level because they'll all vary a little bit, but that's kind of the for condenser mics because they all have their own kind of preamp in it, so no telling what you'll get out of there. Preamp, what's that, Dan? Well, let's start talking about that. So the preamp is on the input circuitry into Q-SYS, this is where we have to take the signal that's coming in and we have to increase its gain so that it matches the same as all the other signals coming into the system, right? So in this case, it allows us to adjust those levels or turn down those levels if they're too hot a little bit. So we have that ability to do that. And so as we move across there, what you do is you have an input device goes in, you have an analog preamp that would be, anywhere from 0 to 83 dB ish on our CMIL4 cards and associated inputs that are similar to that. The analog to digital converter, it goes through. So now this is the point when it changes it from analog signal to a digital. And then we're now in the digital domain. And this is very typical across most DSPs you'll see, or anything that's doing digital signal processing, right? The key to remember this is the preamp is so important in this case because we want to take this signal and we want to give a clean and accurate signal before it goes into conversion between analog and digital, because it's going to make samples and go along the way, and we want that to be clean. So analog to digital conversion. Digital audio systems sample the analog waveform. So just think about, if it's making samples along the way, and what happens is if it misses a sample, and if the signal is here and the next sample is here, it's like, oh, it can draw that line and assume between there. But they sample the audio waveform, and the sample value is scaled then in comparison to the power supply voltage. Understanding this conversion requires a new unit of measurement, and we call that dB full scale. So you'll notice in Q-SYS that all of our most of our meters are in dB full scale. Our input meters are in dB full scale, not in dBu, because we're measuring that signal after it's gone through the preamp, right? As you adjust the preamp, you want to see what that level is. And once it goes through the preamp, it goes through the analog to digital. And so we're measuring it at a dB full scale level there. In dB full scale, what you'll understand there is once you're in the digital realm, 0 dB is clipping. And there's nothing beyond that. It clips at 0 dB. And therefore 20 dB down from headroom is negative 20 dB full scale. A lot of folks, and I'm very guilty of this, when I started working into the Q-SYS platform, a decade or so ago, I wasn't aware that their meters were in dB full scale. Some other people have their meters in dBu. And so you typically would set for 0 dB gain or somewhere around there, 0 to plus 4 dBu is a good nominal level to bring systems in. Well, I'm like, man, I've used this mic a bunch and I've never had to add 60 dB to get there. And, normally it's about 40. And then later I find out, well, these are dB full scale and I was nearly overdriving the input on everything. So very important. If you take one thing away from this, when you're operating in Q-SYS, and you're looking for a nominal input level, negative 20 dB full scale is there. So we want to allow 20 dB of headroom, simply add the preamp gain to reach that level. Now you'll notice here that the meter says dB full scale. and you're doing your preamp gain right here. Now, after it goes through the analog to digital converter, you do have a digital gain that if you needed to give something an additional bump up, but this is the key one that you want to adjust because this is making sure the waveform is at the nominal level prior to going through the analog to digital converter. So that's important that you're manipulating preamp gain and not digital gain after the fact. So we'll go on here. So microphones have their own noise floor based on ambient level in the room, right? This is where the extra challenges come in, right? The fact that it's not just the electronic noise associated with the circuit, but it's also whatever ambient noise. Now we're bringing in fans and air conditioning and building vibration and who knows what, water running through the plumbing in the wall. Who knows what other things are going to be brought into there. So what we'll do there is we simply add preamp gain till we get to the nominal level. So essentially you're having someone just talk into a microphone at a normal level and a normal distance. And you want to do that for every single microphone input. There's no way to fix poor signal to noise ratio at the mic with the DSP, right? So if there's just too much room, the AEC algorithm does have a noise reduction, but that noise reduction is really for steady state noise. It's not, a lot of people think, oh, well, that's to get rid of, if Bob the loud talker is in the room next door to the conference room, we'll just turn that noise reduction up. No, it's got to be, it's got to be a hum. It's got to be, it might eradicate a lawnmower outside the window or something like that. But speech, it's not going to do that. It only removes steady, constant state noise. The AVIXA standard for speech intelligibility in a microphone is 15 dB. So we need to be at least 15 dB above the noise floor at our nominal level in order for there to be intelligibility. And remember, if it's not intelligible at the mic, you've got to address it back at the source. So let's take a look at what that looks like. So if the nominal level of 20 dB has been achieved, but the noise floor is above negative 35 dB full scale, so negative 20, we go down 15 dB. So in this case, it's at negative 31, right? It's the minimum signal to noise ratio for speech intelligibility hasn't been accomplished. And the way you test this is have a talker start talking into a microphone at a normal distance and level, adjust the preamp gain, and then the peak input level is when the talker should be silent, they should stop talking, and the noise level should be below negative 35 dB full scale. If it's greater, then you're going to have to adjust something in the room. If you increase the preamp gain to make the microphone signal louder, you're also increasing the noise floor just as much, so that's not helping. So you have to address that at the source if you have issues with that. And the source could be noises in the room, acoustic treatment, whatever those are. I know those are hard conversations, but sometimes you just got to know that you have to address it that way. So microphone, let's see, did I hit forward? Yeah, so this is what a proper signal would look like, right? Have someone talk in the microphone at normal level. And when the person stops talking, if you can see in this example, it's negative 43, so it's well below that 15, then you should have, by AVIXA standards, a signal to noise ratio that works well and performs well in this space. Microphone equalization. So typical microphone signal path, and by the way, I say this goes the same for DSP programming as it does for control programming. How many times has someone seen their control programmer open up someone else's code and go, this person doesn't know what they're doing, or really what they're saying is this person doesn't write code the same exact way I do. So I always say DSP programming and audio and control program, it is artwork in a way, right? And there are rights and wrongs, but for the most part, if I tell everyone to draw a car, they're all going to draw a car, right? There might be varying year models or makes or things like that, but it's a car. So we're not here to debate, the nuances of how to EQ and things like that. We're just going to talk about the kind of some of the best practices and rules of thumb, and there's going to be places where you may deviate from that. So typically what you'll see is a high pass filter at the beginning, any type, any slope. We don't have any hard stance on that. That's up to you. You can do more research on those and see what you would like. But essentially, we want to roll the low frequencies off, especially on a microphone. Anything, if it's under 60 to 80 dB roll off, I mean, all of that is just low and unintelligible. You can even, for some conferencing applications, you might roll off below 100. If you've got really bad HVAC in the room or something like that, you can kind of bump it up to closer to 100 if need be. The thing to remember there, I mean, is there's not going to be a lot of human voice that falls between that. And then you've got a parametric EQ, and this is going to be to remove any problematic frequencies in the room that the microphone is experiencing, right? So maybe there's something about the reflections of the room that at 1.2K, you need to bring that signal down just a little bit to keep the mic from having any feedback or something like that. So parametric EQ. Oh, well, I forgot the low pass. Let's go back. Low pass is a similar thing. You can set this around 16K. The human voice range is well below that level, unless you're really a super soprano singing high. But so typically a low pass filter, you want to set that around 16 kilohertz. You could go to 8K if you need to. You're just going to be kind of narrowing that band. If anyone's been in conferencing in DSP for 10 or probably 15 years or more, you know that the early AEC blocks were very limiting in how much bandwidth because it was easier to process that amount. And some of the big breakthroughs around the turn of the century, like 2005, stuff like that, was that we had full wideband and had the ability to do that. So, but just think about what your vocal range is, because it is mic. It is this. We're not miking instruments here. If you are miking instruments, that's a different story. We'll get into that, or that'll be a topic for another time. So parametric, consult your microphone manufacturer for exactly what curves they might recommend. Nobody builds a perfectly flat microphone, meaning exactly how the diaphragm moves is exactly what it's going to reproduce there. And there's going to be nuances to the cardioid pattern or hypercardioid or whatever the pattern is. There's going to be things that you want to EQ out for that microphone. So the manufacturer typically publishes that, and you can use that as a guideline. And you can use separate EQ components to EQ your mic and EQ your room. So you'll see a similar chain like this when we get to the output side. Typically, but this is what you'll see on the front end side there. Remember, if you need to emphasize, if you're having issues with speech intelligibility, you can emphasize a little bit in that EQ in the parametric vowels to land between 250 and 1,000 hertz, consonants between 1,500 and 6,000. Your sibilants and STs and Zs, those land between 5 and 7. And I've actually seen in like performing spaces and stuff like that where, it's an all hands meeting room, things like that, where you'll give it a little bit of a bump around, somewhere between 5 and 8, depending on how the room is, just to help that intelligibility of the speech there a little bit. So identifying feedback frequencies. So in the Q-SYS software, we have what we call a notch feedback controller. And so this notch feedback controller lets you identify problematic frequencies, and you have the ability to go in and use that as a tool to identify, hey, what should I set my parametric to? So we show it in the signal chain here. They are a pretty DSP resource intensive device. So you could leave it in your signal chain, or you could put it in your set of test tools that are part of your Q-SYS test tools in a design, and then just kind of use a probe to probe each signal and see there. Because if you had like 12 mics in the system, having 12 notch feedback controllers wouldn't be a good idea. But the way you do it is you'll set the fixed filter count on that to 0. And then you'll set the dynamic filter to 5-ish, because you got a 5-band parametric, most likely, or a 4-band. And you want to set the frequency range on it from 80 to 20 hertz, and then go find the threshold. So here's what that looks like. So just like I was saying, you set your fixed filters. So these are filters. This is a tool that you can set into a system, and then it will automatically notch out the things you want to do. Now, the true audio people are going to be like, well, if you set the room up right, Yeah, but if it's a public space or, there's places where this could be, and accidents happen, people point microphones in the wrong place and things like that. So, but you can see here, so we've set fixed filters to 0 because we don't want any permanent filters in place. And then dynamic filters are filters that just get dropped in. And then based on this reclaim time over here is how long that filter, once the feedback condition is gone, it will take 30 seconds for that filter to dissolve and go back away. So that way you're not just loading up with a bunch of filters that aren't needed at the time. And this works remarkably well and relatively quick too. So can be used on the outboard side, but like I said, we're not going to deep dive today into the notch feedback controller, but it's a tool that you can use there. So now knowing that, now that we have this information that we've got problem frequencies at 150, 210, 600, and 800 Hertz, how do we address that in the parametric? Well, we go over here to the parametric and so what we go do is we've got problem frequencies close together. So there's no reason to put a notch for each one of those. So maybe we would go right between, it's a little hard to see, but we've chose about 700, or I'm sorry, the first one is about 200 Hertz, right? That was between 180 and 220. We had a couple of bumps. And instead of bringing it down, I mean, if I go back a slide and we look, instead of bringing it down, 12, 13 dB, like the notch feedback controller it's a little reactive, right? It overreacts because it needs to stop the feedback immediately. But what could remove the feedback is just a nice little 3 dB, 6 dB maybe dip. Just bring it down slowly and see when you can get that feedback to stop. And you can see we've got one of them set here at 200, and we've got one set at about let's see, 700 or 568 there. Kind of handle that 600 to 800 problems that we were seeing. Now we have two types of mixers, two major types of mixers that we use in Q-SYS. We've got a matrix mixer, which just allows the user to assign what goes where, right? And then the output level is simply a combination of all the things that have been mixed and sent to that output to go out. Auto mixers are designed require no real operator, right? Mics are typically ran through an auto mixer to then a mixed output. So it handles all of everything that needs to happen in there as far as gating mics on, gating mics off, and things like that. They do have optional direct outs so that you can send it to a corresponding mic signal. And we have two different algorithms that decide which mics pass to the output. We'll talk about those when we get into auto mixers. Let's start first with the matrix mixer. The matrix mixer goes in and has cross point controls, right? So essentially you've got input signals coming in down here. And if you want this microphone to go out to this loudspeaker or this downstream device, you would set this cross point to 0 or some fashion thereof. You assuming all inputs are adjusted to nominal, right? So this is where gain structure comes in. If they're all set to the same coming into the DSP, then we know that everything coming into the mixer there. A lot of times, if I'm helping on a support case or something, and I open up a file, and someone's, without even being live in the room, I can tell that their gain structure on the input side is wrong because this matrix mixer will have -3, +9, -6. I mean, like it'll be all over the map because the signals aren't level coming in. If I have mixed mics and I have a program source and I have other stuff and they're not all the same level coming into this matrix mixer, then we've got to micro adjust them there. So for the most part, your cross points should be set to 0. If there's big disparate difference between lots of cross points, just know that you might want to go back and check your gain structure there. The other thing on the matrix mixer is you can set it to have cross point mutes if you want, and essentially -100 turned all the way down is off, considering you're not making that cross point. Auto mixers used mostly for conferencing and for speech and reinforcement, and they have an adaptive threshold gating, right? So we recommend a max number of open mics or NOM of somewhere between 1 and 3. And one of our engineers on the team says, if you've got more than 3 people talking, it's no longer a meeting, it's an argument. So that's where we're at on that. So let me see, I went the wrong way there. There we go. Um, no, nominal attenuation settings should remain somewhere around defaults. If you're really getting into it, if you really understand how to use one of these, you may be able to work with that. Rarely, if ever, do you need more than 3 mics. The more microphones that are open, the harder it becomes to manage feedback, right, in the space. So the channel manual gain, this manual C is allows for a channel to be removed from the auto mix, and it's excluded from the count of number of open mics. So this might be the head of the table, the most important person in the room, whatever the case may be, right? Or it might be the lectern microphone is always set to be on, but the microphones around the other space for Q&A or this or that, even if they're beamforming mics, those may be set to be auto, to where you'd want to auto mix those as well. So, and those would be in the nom, and the other one would be on all the time. So. If you have, in this case, with a gating auto mic mixer, this is one we started with here, you'll notice that with one mic open, we have no real attenuation being done. You can see over here is our amount of negative gain that we would apply. But once you get a second microphone open, then it adds 3 dB to the output, right? Because when you mix two signals together, it typically the additive process ups the output volume a little bit. So what you do is we bring that output down by 3 dB. Now, we already said we never recommend a number of open mics, but if you had 4 open mics, when you got to 4 open mics, what it would do is it would add 6 dB of attention there, and so on and so on. So when you get down to 6 mics, you're going to get a few more and all of that. So the gain sharing auto mixer is a little bit of a different animal. It's based on the Dan Dugan algorithm. We're not licensing that algorithm, but it's based on that. And this has a maximum gain of 0. And so all the open mics will share whatever total available gain is, right? And so when we look at what that looks like, if we have one person that's talking, that mic will be granted all of the mixer gain there. Or in this case, as far as the diagram is shown, we have 1, 2, 3 open mics, and we've given gain to those. So essentially we have all the knobs turned. It's like someone had a mixer, right? So the faders are all down, and mic 1 talks, so I slid fader 1 up, and I let more of that signal go through. Oh, mic 3's talking, now mic 4. If mic 4 stops talking, and mic 2 does, I'm going to bring that gain up. So it's truly more like someone's auto mixing rather than attenuating like it does on the other path. So as the number of talkers grows, each mic will get granted more and more. We recommend that you use gain sharing mic mixers. I use them primarily only for like a speaking dais or something like that. I typically never use these for conferencing, but if you are going to use them, about 8 to 12 microphones is about when this becomes not efficient, right? And that's when you would want to look at the gating mic mixer. So let's put it all together. We need to often mix matrix and auto mixers in the same signal flow. That's important, right? So if we look here, we've got all of our mics coming in, they're going through a gating mixer, and we put that into a mixer. We've got our program audio down here. We calibrated those all to negative dB full scale, 20 dB full scale. Those come in and those hit the matrix mixer. Then we may go out to, who knows, this says main speakers left, distributed speaker mix going out to the hallways. Maybe output 4 is going to a recorder, right? So we could choose and pick and choose what's going to each one there. Microphone dynamic processing. So let's talk about what that's going to do for us there. Compressors generally will level off loud talkers. They can be a little bit aggressive in their operation when you're doing just spoken word, kind of more designed for less aggressive for vocal performances, right? So the idea is that with a compressor, mentally the way I look at it is you still feel the impact of it there, but we pull that signal level down just by saying, hey, look, we're going to limit that. It doesn't solve a problem, is one drawback for quiet talkers, right? So if you've got a quiet talker, the compressor is not going to be helpful with that. Automatic gain controls, AGC blocks that we have, helps for quiet talkers, help for loud talkers. It's slower than a compressor, and if it's not properly set up, you can increase your noise level. You can increase level based on noise in the room. So we do have a deep dive we run about twice a year on dynamic audio processing, and we do some great examples and talk about the AGC, the compressor, and things like that. So if some of this doesn't make a lot of sense to you and want to dive deeper on that, keep your eyes peeled on the deep dive webinars for those. What's wrong with this picture? I like to say we're paying our Visa with our MasterCard or whatever. So essentially we have a gate before a gating mic mixer. So that's just gonna cause a tremendous amount of issues. I know early on in my career, I had a microphone that had to share a conduit with electrical and it had a hum and a buzz on it. So I'm like, well, it keeps gating on in the gating mic mixer. So I'm just gonna, and I couldn't get it out on the front end. See, I didn't solve the problem at the source. So it created a lot more problems downstream. So then I put a gate in front of the gating mic mixer. Well, then it would delay. It's a bad thing. Here's the rule of thumb. Don't put gates before your gating mic mixer. And don't put user volume controls before the gating mic mixer either. That's another no-no. So let's just see real quick. Did anybody drop anything in the Q&A? We've got chat there. Okay, no webinar chat. Just want to make sure we're all good here. All right, perfect. So the next thing we're going to talk about is introducing AEC into our system. As you can see, we've got just a basic signal flow here. I mean, I wish every system was this basic, but microphones in, they go through an echo canceller, they go to a gating mic mixer, and they go out to the VoIP, the USB, the POTS line, telephone, whatever it might be. And then, from the far, our local path for audio inside is any audio sources that might be coming into the system locally, go through a mixer, and then we have the returning audio from the far end of the call coming back in. And then right before we go out to our amplifier to go out to our loudspeakers, we pull our reference. Now, typically there would be volume controls in here, things like that. So the thing to remember with the reference is you want it to track the room volume that's going up and down, and we'll talk about a little bit more of that in the coming slides. But let's just focus on some of the conferencing terminology. So latency, it takes a little while to do all of what we're doing with the AEC, right? So it does need some look ahead time. So you have a little bit of delay type, depending on which cores you're using. So the Core 8 Flex, the Nano, the NV32, the Core 110, and the Core 24F, from the input to the conference output is about 32 milliseconds of latency. And then input to the reinforcement output, and we'll talk about the reinforcement output in just a little bit here because there's been some questions on that. And hopefully I'll give you some guidelines, is 21.4. All of the other cores, you get into the server cores, the 5200, things like that. 26.7, they obviously have a little bit more processing power. They can manipulate this data faster, or 10.7 milliseconds to the reinforcement outputs. Tail length, this is important. The latest tail length is the latest possible reflection that can be canceled. So most DSPs across the board have about a 200 millisecond tail length when they advertise. For instance, when we advertise a Core 110, we say 16 channels of AEC at 200 milliseconds. We're one of the very unique DSPs that I'm aware of, unless somebody else is doing it these days, that you can adjust the tail length of that AEC algorithm. And the tail length is essentially how long is it listening to the room before it does its subtractive process, right? In AEC, the microphone is just a dumb device, and it doesn't know if the sound pressure that's hitting its element is your voice that needs to go to the far end, or if it's the audio coming out of the loudspeaker, right? And if it plays the audio coming out of the loudspeaker, which includes the far end audio, it's going to send that to the far end, and they're going to hear a very predictable echo. And so tail length is how long it listens before it kind of does that subtractive process. 200 milliseconds for the industry standards. We have the ability in Q-SYS to be able to lower that down to 100. If you had a very well acoustic treated room, you had maybe microphones or even headsets on people with cardioid elements or supercardioids, that's when you might be able to go down to that 100. So 300 and 400 are also options, so that if you get into that reflective space where the architect beat the AV designer to the room, and there's a curved hard deck ceiling above a marble table and three glass walls, that's going to be a really reflective space. So when someone talks in that room, pop, 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 we're going to have a lot of reflection in there. So we need it for it to listen longer. Now, the thing about that to remember is it does consume more resources. So check your guide in that Q-SYS help file, and it'll tell you about, hey, if I have a Core 110 with 16 channels at 200 milliseconds, if I go to 300, I'm only going to have 12. And if I go to 400 milliseconds, I'm only going to have 8 channels of AEC. And at 100, you do get 24, but I wouldn't make designs based on that. So, but you can find those guidelines based on all of the new cores that come out and all of that in the help file. Excuse me. This part really chokes me up. No. Let me get a drink of water. All right. So conferencing terminology, right? This you kind of see a pattern here. As we talk about something, we talk about the terminology, and then we go through what it is. RMLR, so reference to microphone level ratio, is the difference in level between the reference signal and the resulting signal at the microphone. So what you're looking at there, so RMLR is you're looking at equals negative 20 dB, negative 30 dB, subtracted by negative 30 dB is going to give you a 10 dB difference, right? So that's AKA the return loss coming back. So it's essentially there, it's happening in the, it's also, echo return loss is what it's also known in other non-QSC DSPs. Residual echo suppression is the same as nonlinear processing in other DSP platforms. And what this does is after the algorithm runs once it runs the signal through, this is where we're going to just add a little bit of extra. It's just a little bit of error correction after the FIR filter and the AEC has done its job. Voice lift. In larger rooms where the near end microphones are sent to speakers in the near end, we would use is the term that we use for that, for voice lift. Mix minus, in larger rooms where you have distinct speaker circuits, right? You have multiple speakers. Say I have a 20-foot long, 30-foot long boardroom table, right? And I need people at the other end of the table to be able to hear me just in a normal meeting, even if we're not having a conference. But then when we go into conferencing, we need to do, or even in that case, what I might do is microphones at the south end of the table will be lifted into individual speaker zones along the way. So if there's 5 speakers down the way between the front of the table and the end of the table, I would have none of the mic at the head of the table in the first speaker. I might have just a tiny bit of it in the next, and then a little more in that. And I get to that 5th speaker down the row, and it might have, a considerable amount. And the also thing to remember too, the term voice lift. So many people think that a microphone's not working if it doesn't sound like Sunday at the Monster Truck Rally. Like it doesn't need to echo. Like if a perfect voice lift is when the person speaking into the mic doesn't realize that it's being lifted in the back of the room, yet they don't have to speak loud in order for the people in the back to be able to hear naturally. So a lot of things come into play with this. You got to set delay right, and the amount of that, but just some terminology there on what we're doing, and we'll go through it. Q-SYS conferencing signal flow, we talked about that. Local microphones go through the AEC, we go through a gating mic mixer, and we go out. And then the far end, the program sources, and the far end conferencing audio get mixed together, and they come out of the local loudspeakers, and that's where we get our reference from, is that last point before the loudspeakers. Microphone processing typically applies equalization, compression, AGC for consistency and level like that. Best practices is you would apply these after the AEC algorithm. Never put dynamics ahead. This should have a big X on it. This is the wrong picture. But essentially, best practices, you bring your mics in and you'd want to do, yeah, I got to fix that one. I'm make a note here. So you never want to put these dynamics ahead of that. So anything that's going to, if you had to, you could certainly manipulate it there if possible. Most important factor in successful AC is having the proper reference. So when no voice lift, the adage is whatever goes to the loudspeakers will go to the reference. So that would include all the far ends, programming sources, especially if they're being routed to the far end. And never put a microphone signal into its own reference. It's going to sound like somebody's underwater if you do that. Assuming you've already brought all the microphone signals to negative 20 dB, so you've done your proper gain structure on the front end, nominal, and you're achieving at least 15 dB of intelligibility. We're going way back. We're going 30 minutes back in our discussion here, but yeah. What you would do is set your amplifiers to a minimum level or set the output block to a max RMS gain, set the max RMS gain to negative 40 dBu if there's no controls on the amp. Using the preamp analog gain, bring all your program sources to negative 20 and leave the program sources at unit gain. So with a calibrated source, bring up the amplifier to a max RMS settings or the max RMS settings to a comfortable listening level in the room. So sorry, I just said a lot of words there. Let's go back through what we're talking about here. So first off, make sure everything coming into the system is set to negative 20 dB full scale. And then what you want to do is take, it says a calibrated, but you know, if you're setting up a performance venue, you're absolutely going to have a calibrated mic and you're going to be bringing that into some type of test equipment and do that. But if you're just setting up your everyday conference room, the dB meter apps on your phone work really great. That's, you can set that down. And the idea is you want to set the room level to about negative 70 dB. And why is that number so important? Average speech, if just two people are talking and you put a dB meter out between the two of them, most human speech level, aside from my grandma, it's about 70 dB or it's about 65 dB. And so when we're in a conference call, we like to have about 3 to 5 dB more than what is normal, because we want to kind of feel, okay, wait, so it'll draw our attention to if it's a video conference or things like that. So typically what you want to do is the nominal level of the room, when the microphones come out of the loudspeakers, when the program audio comes out, it's a little bit above the normal human voice of around 65, so we set it to 70. Then we make a test call and adjust the far end gain controls to receive a level of negative 20 dB full scale. With the listener at the far ends, the AEC can be then fine-tuned. So, you'll make a call, and you'll talk, and then let's have someone at the far end listen to the room, and they can make suggestions. So really what you hear in the room that's the hardest thing I think about setting up AEC and setting up a conference room is, you have to have somebody on the far end listening and telling you. Ideally, the best thing is someone's remoted in and they're adjusting to fix what they hear and what they don't hear. Conferencing system setup. So if we look at the AEC block itself, down here in the bottom right, we have noise reduction and noise reduction enable. Like I said early on, this only reduces steady state noise, it can color the microphone slightly the more noise reduction that you add. So even in the properties, you can go in the properties of this. Right now, I think it's set from 0 to 10 dB, but you can go 0 to 20 or 0 to 30. You start removing that much noise, you need to really evaluate whether this is a space you should be doing conferencing in. And then the next control over here, the reference to microphone level. This is the easiest meter and easiest thing to set up in Q-SYS, right? I think when it's green, the gain is proper. The level of reference that you're applying to the algorithm is proper. If it goes above that, it'll go yellow and then red, and below it, it goes yellow and red. So if it's too high, you actually use the reference gain here to bring that down a little bit. If it's too low, you use that reference gain to bring it back up. Now, if I have multiple mics, let's say I'm doing, I'm bringing 8 microphones into an echo canceller that has a single source brought in. What I'm going to do on that, I have one AEC that's bringing 8 mics in, but I'm just sending a mixed output of those mics out of there. I'm sorry, I have a shared reference. So one reference I'm bringing in, I'm not doing mix minus, so I'm bringing a single reference into the AEC algorithm. What I'm going to have is I'm going to have multiple of these these gain knobs across the bottom. And the way you do that is you would just raise the amount of reference coming in till all of the microphones are at least green. Some may be above the green. But you want to make sure that that the minimum at every mic is that everyone is at least at green or above. And then you would use these faders to pull down each one. And the reason for that is, if I have 4 loudspeakers in a room and 8 mics, some microphones are going to be closer to those loudspeakers than other microphones are. And so they're going to need more or less reference based on that. So that's kind of what you're setting there. That's what that control does for us. So the RMR, the residual echo suppression, the RES here, sets nonlinear processing. So this is just a little bit of, like you said, think about this as if you understood the tail length that we're listening for 200 milliseconds, this is where we're trimming off anything that during that 200 milliseconds that didn't get subtracted out of the signal. Now, one thing to hear, the more you apply of this, the closer you're going to get to a half duplex. So just be aware of that. And you want to test your double talk condition here. So double talk is if I'm talking on a call and the person on the far end calls, if there's 3 or 4 people on a call and out of my room when I'm talking and someone else on the conference talks, if my voice gets damaged or it's not coming through clearly, then you're into it. You're losing your ability to have independent conversation there. So increase your RAS to handle that. So what if there's still significant echo when we're all the way done with all of this, right? One of the things you want to do is make sure that your signals aren't misrouted or looped somewhere. Sometimes I'm really going to date myself here. I remember the days of the hard codecs, big, Polycom, Tandberg, Cisco. I really dated myself saying Tandberg. Would have a reinforcement out that might be where they're bringing the audio in, and that's going to cause issues and things like that. That's going to direct couple. So you just want to make sure that mute microphones. What you would do is go through and mute your microphones to verify that it's really echo and not just direct coupling, meaning you've routed something misrouted in there. If the echo is still there after you've muted all your mics, then mute microphones. Then start muting your inputs until you figure out which source has been routed incorrectly. And if there's still residual echo suppression, check out our new line of Q-SYS acoustic treatment. No, I'm just kidding. But essentially, if the tail length is at 100 milliseconds, by all means extend to 200 because that's a kind of an industry standard. If it's at 200, it's not likely that it's going to just improve by going to 300 or 400. 300 and 400 is really for really big rooms and rooms with a lot of reflection. Like if you clap your hands and it's clap, 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 you're going to want to, that's a room that you may want to look at 300 and 400 for. So don't just jump to that because you learned it on this webinar. Oh, that's what 300 millisecond does. Make sure that it's a reflective space and you've checked the other things first. So conferencing system. So you want to go through, let's see, I want to go back through. I think someone's messed with my slide deck here. All right. First thing you want to do, you want to go through, if there's still a recommend reduces there. Once we have a basis for a conferencing setup, you've got the AEC block, the output structure, repeat this test call for every conferencing type there, right? So just because we had a good call with the USB connection doesn't mean that the VoIP connection is going to be good too. So if you're doing codec, if you're doing POTS, if you're doing, whatever type of conferencing, make sure you do test calls with all of them and test it out there. I know I'm guilty of, back in the day, of starting with the lowest common denominator. The noisiest one you would connect to would be a plain old telephone system. And I'm like, well, if that sounds good, the rest of it will. Don't take that for granted. So after the mix, what do we do there? So typical of design elements that you'd see after the mixer, might be some equalization, could be some user level controls, could be limiting, could be delay. You'll typically see peak limiters on our output versus compressors because what we're trying to do is prevent something from overdriving a downstream device, and we just want that to happen right away and quickly there. Um, so EQ in the signal chain, in the output signal chain, is for your speaker EQ and for your room EQ. So every speaker, just like microphones, most manufacturers will provide some type of curve or notches because there's no such thing as a perfectly flat speaker that reproduces exactly the sound wave that it's supposed to. So you may need to use that. If you're using Q-SYS speakers, QSC speakers, we call this intrinsic correction. And so if you have our speakers in the system and you're using our digital amps, you tie this amp, the speaker block to that amp, and it says, oh, okay, so it needs this notch and it needs this. And it also sets limiting and all of that. If you're not using our amplifiers, but you are using QSC speakers, you can make that an inline block that actually adds that little bit of EQ for you. You may still want a parametric in there because that's when you're going to start getting to the room EQ. So you need a few bands in your output side to be able to adjust the room EQ. There's going to be nuances about every space that are a little bit different, reflections and things like that. So that's where you'll want to use that. So parametrics on the front end for the microphones are really to notch out problematic frequencies related to just that particular microphone and then where it's at in the space. And then on the outboard side, we're just using it to account for the size, the shape, and the reflectivity of the room. Our user controls better, gain controls better on the input or output side of the mixer. The simple way to decide this is, does the user need to control the level to all outputs pre-mix, or does it need to just one gain to rule the or do they want just one level for the output? Now it depends on the room, depends on the user experience, and things like that. My general rule of thumb is, don't give multiple places where users can destroy the gain structure. If your customer doesn't want just one main volume control of the going out of the room, you may have a conferencing volume control that's pre-mix. But you really should never give someone a volume control to a sound they can't hear. So I wouldn't give a gain control for the mics going to the far end of the conferencing because I'm not in that room and I can't hear that. Those people should have a gain control on the audio that's coming in, as kind of their program audio. So just some things to think about as you go through that. Output limiting. So this will prevent a signal from going beyond a predetermined level. It prevents clipping of any downstream devices and prevents overloading of amplifiers and other things that go down there. Peak the limiter block, the default threshold is 0, but let's take a look at what's ideal. So below the threshold, the input signal is pretty much unaltered. It's not going to do anything to it. But once you get to that threshold of 0, the limiter is going to take a little bit of time to react and it's going to pull that signal down. So you can see in this graphic that it kind of shot up to 6-ish, 5 or 6-ish. And then by the time it pulled it down, it kind of pulled it down right there. What we recommend is you may want to set this to like -3. And so it's going to kind of limit how much that over and just give you a little bit more headroom in there. So reduce the threshold by dB, it gives it a little bit more margin before it clips, less likely to cause issues. Amplifier limiting. So QSC amplifiers are limited automatically if the speaker blocks are configured correctly for each output. Few types of limiting that we include in there is AC limit, so clipping before the amplifier, at a stage before the amplifier. Protect is a limit, limiting due to low impedance. Low impedance could be the wire got shorted together. That's really low impedance. And limit is combused based on load type. So if I'm just pushing, I have too large of a load out there, that's going to tell me that there's something else going on out there as well too. Output gain structure. If you're not going to a QSC amplifier, ultimately you've got to convert the signal, the digital audio back to analog. And in the limit example, we saw that the clipping happened at 0 dB. In keeping with our 20 dB gain structure, the digital gain should be left at 0 dB. And so what you would do is on your output gain, um, analog out, RMS max output level when analog gain is 0. So you want to set that digital gain to 0. You'll notice that we've got a peak output level in the analog world after going through the analog to digital converter is at, right at total, at perfect 24 dBu. And then down here, you've got about the same thing there. You've got right about 0 dB full scale. So you got dB full scale prior to digital to analog conversion, and you've got about 0 dB or plus 4 dBu-ish going out there, or plus 24, excuse me. What if the next device in line? Remember I said that consumer devices they don't want to see plus 4 dBu. They want to see like negative 10. So what you do there are negative 8. Consumer line level is about negative 8 dBu. And so what you would do there is you would come in and you would adjust this output gain of your analog. So we go through the digital to analog conversion, and essentially we're turning the volume down on the output so that we don't overdrive the input of the next system down. So assume 12 dB of headroom and your maximum input level of plus 4 dBu. Now we reach 7 dBu when we're at 0 dB. The idea is you've set all your gain structure that the loudest this is going to be is right here at 0 dB full scale, and we can turn down that volume of the next downstream device. Now, if that's an amplifier, you're going to have amplifier controls on it to turn it back up, but that's where you want to just do it there. Sometimes you must feed a microphone level device. Maybe the only thing you've got is a mic input on a whatever. If that's the case, make sure that the device doesn't have phantom power, because we don't want to bring phantom power back to our Q-SYS output circuitry. But you have the ability here to take and turn this output gain all the way down to where you're matching that negative 40 dBu that would be an input looking for a mic signal. So it certainly is doable. Nope, I don't want to upgrade my Apple software. Decreasing output, so output gain structure. So just like before, if we have a noise floor of a circuit, if we have professional audio level, we're going to have more signal to noise ratio. We're going to have a better signal noise ratio. So we have to go, this is why it's important with consumer line level, is that, you have less noise floor, and then microphone, you even have an even smaller amount of noise floor. So we're going to review the most important concepts here. Calibrate all your inputs to make sure that they're properly set up and everything is coming in at about the same level. Trim in microphones, you're going to want to trim the high and the low frequency noise out, anything that's outside of that with low pass and high pass filters, and then put a parametric EQ in there to add any suggested curves for those mics. You can use a notch filter or a parametric EQ to trim out any feedback, problematic frequencies that the mic's having in the room. And the notch feedback controller can be used as a tool to kind of help you identify that. Microphone dynamics, automatic gain control or compressors can be used to get consistent levels from a wide range of talkers. So that's where your compressors, all of that stuff there. Do not use lever for auto mixing. Do not place user level controls or gates ahead of auto. We did definitely talk about gates, but we didn't talk about level controls. You don't want to put a level control of oh, I want to turn this mic up. Well, it's going to be the loudest signal all the time going into that auto mixer, and you don't want that. Also, use fewest user gain controls as possible to get job done. You might have several in the signal path, but only expose to the users the minimum that they need, so that they don't end up turning one down here and then turning this up past the auto mixer, and you can really get into some problems. Output limiting, QSC amplifier limiting applies automatically when you're using our digital amps. Use peak limiter component to prevent any output from clipping if you have an analog out you're going. Proper gain structure is negative 3 dB full scale is a good threshold limit for that. Make sure to calibrate your outputs depending on what they go to. And yeah. So you will get a troubleshooting guide. It's a two-sided page that prints really well on 11 by 17. So you can print that two-sided, fold that up, put it in your toolkit or your backpack, and you kind of got it there. And it kind of walks through just like basic setups for gain structure. And the other side of it is AEC. So great stuff there. So that's all we've got for today. I did not see any questions along the way, but maybe I missed them. Let's see, more Q&A. We had one Q&A. These are great sessions, but I missed last week's. Is there a place to view the recording? Well, Anthony, I'm glad that you said that. So yes, here's a secret that a lot of people don't know, is if you've signed up to attend it, but just didn't make it, you will within a week or a week two. Right now we're getting it. Marketing is teams up with me to put the web notices out and to get the follow-up emails out. So what you'll find is usually they're out within 3 to 5 days after the deep dive. But right now we've got a lot of folks preparing for InfoComm. Plus, I think we have an Activate coming up in June. So it may be later this week. So it may be, and we had a holiday and all that. So, but yeah. Stanton Horton says, can you explain the preamp sensitivity and why it changes when adjusting gain? So let me look at the preamp sensitivity. Let me see if I can find a slide so we can talk about that. So I can at least point and grunt. Maybe easier. Let me roll back on that. And I appreciate everyone as I ran a full hour on this. We used to do gain structure and then AEC in separate ones, and they were both about 40 minutes. So let's see. All right, let's see let me go ahead and share this again, and I think that'll help a little bit. Share my screen. All right. So I believe the question was, did I end up sharing? No, I didn't hit the share button. There we go. Explain the preamp sensitivity and why it changes when adjusting the gain. So the preamp sensitivity right here, when you're adjusting the gain up or down, that preamp is how sensitive that is to the signal that's coming in, right? So if I have a low level signal and I turn that gain and I turn the preamp gain up, essentially that preamp sensitivity is going to become more sensitive to any signal that's coming in there. So that's why you see those two, and they typically appear to be inverse of each other, but you just have to look at the numbers and why it's working that way. I may see if I can, Stanton, I'll boot up a live version of Q-SYS, and we can talk about what that, I can actually show that a little bit. So let's change this core here to we'll do the good old core 110. I'll bring that over here. If we look at this block and I emulate, all right. So what I think what you're saying is, as you bring up your preamp gain, you'll notice that the sensitivity is inverse, right? So it's how sensitive it is to the signal that's coming in there. So when you have so that's kind of the 100-foot view on what that's doing for us there. So it should change because we're making the input either more sensitive or less sensitive to the signal coming in. Chad Meese, apologies if you covered this and I missed it. In the QSC amplifier block, what will sending a pilot tone tell you? Well, glad I have this open. Let's do, so the pilot tone, and I'll just do this real quick. I'll just throw an amplifier in, say a 2K4, and then we'll also throw in a loudspeaker like, all right, we'll go with the 6. All right, so if I bring this in and I bring the amplifier's output in, I believe what he's talking about here is you've got a pilot tone. And so the way this works, actually, it might even help to see. Let's look at something that's live. That will help out too. So but essentially the pilot tone, we send a low frequency pilot tone below audible, unless you're and a high frequency pilot tone. And what it does is it's sending it out there and it's evaluating the impedance of the line based on what it's getting back there. Okay, let's see here. Oh, there we go. 10.2, and it's enabling access control. It's giving me a little bit of challenge. So that pilot tone goes out, and then we can read the impedance of that line. And so what I'm going to do is I'm going to show you this with, let's see, let's do some audio output. So if we look at this loudspeaker right here, what you do is you go in and you set your threshold. Say anything below 1 ohm, I'm going to consider a short, and anything above 120 is going to be considered it's going to be considered an open condition. So then I would go in and I would turn on my low tone and my high tone, and it's going to analyze that speaker line. And it's going to say, because you may have several speakers tied together. So it's going to say, okay, the low frequency tone is at 15.8. Between low frequency and high frequency, you'll get a little bit of impedance difference, because impedance isn't just a straight resistance. It's inductive reactance and inductive capacitance and how they work. But essentially you'll go, okay, so the normal operating of this system is that the speaker line should be between 15.8 and 19. What I would do then is I would go here and I would set, I might set this level for, say 10 or somewhere right around there, 8 or 10, and then I want to go right above 20. So I might set that down to, 23, right? Or something like that. So essentially, if the impedance of the line, and then I can turn the pilot tones off, but essentially, if the impedance of the line that the amplifier is reading of that speaker line drops below 8 ohms, it's going to give me that, it's going to light this LED and say you have a short, and I'm going to be able to do something about that. If it goes above 23, it's going to be like, oh, wow, somebody cut your wire. You got a speaker that's blown, something, connection came disconnected, whatever. That's the beauty of that. So that's what that one does for you there. So if there's no other questions, I know we ran a little bit long. I do appreciate it, the fact that everyone hung around while we went through this. I'm going to stop sharing. We'll kind of pull back here, but thank you all very much. I know that your time is valuable. We hope you find these. Next month, we've got some good ones coming out as well. So we'll have, on the 9th, we'll have how to choose the right Q-SYS core processor. So in the last year, we've released the Core 24F and then the server cores. So this is just going to it's an overview of all the different cores, the different little nuances and features between them. So that's a great one. Because we have Infocom, we also have some other marketing things. Our other deep dive will be for room suite design. So the one at the end of June is going to be talking about our room suite product, which is you kind of build it with your pieces of equipment and it kind of self-configures itself with the guidance of a technician. So you'll see some of that out there as well. So really appreciate the time, and everyone have a great day. Thank you.